Hello everyone. In this episode we're going to work on another extensive form games which is called a model of limited capacity. Basically we're going to find the subgame perfect Nash equilibrium of this game. But this is a complicated game and so I think it deserves a specific episode. And so here's the details of the game. There are two firms. I'm going to call them firm 1 and 2 as usual, and they consider whether and how to enter a new industry. All right, so the demand function in this industry is given by this demand function 900 minus Q1 minus Q2. Right? So given each firm's quantity level, this is what the market clearing price will be. So they are actually competing in a Cournot fashion, meaning they choose their quantities simultaneously. But before entering to this market, they need to decide how big production facility they want to build. They can build a small production facility or a large production facility. I'm going to call them S versus L. So here's the thing about production facilities. Well, the small production facility requires an investment which is going to cost $50,000 or 50K. If it is a large production facility, it's going to cost much more, $175,000. Well, here the thing is though, if you invest a small production capacity facility, you can produce at most 100 units with zero marginal cost. Well, what does that mean? That means you can produce less than 100 units, obviously, but at most 100 units with no cost. But beyond 100 units, you cannot produce. All right, so 101 unit of production is impossible. 105 units of production is impossible. All right, so I mean, think of this as a factory, and so in this factory you cannot produce. It's a small factory this is, say, a monthly sort of output. So you cannot produce more than 100 units. All right, it's impossible. Below 100, you can produce as much as you like, up to 100, with no cost. However, if it is a large large production facility, well, then you can produce as much as you like with zero marginal cost. All right, so that's it. The question is, do I want to build a large factory so there's going to be no upper bound, or a small factory which is going to have an upper bound which is 100? So what do I want? Well, so here is the structure of the game. Firm 1 decides out of three things. You can stay out, you can invest a small facility, or a large facility. Well, then player 2, firm 2, observes your move. It chooses out, small facility or large. However, if you selected small, again, the firm 2 can stay out, small or large. If it is again, these are all player 2, firm 2 I mean. If firm 1 selected large capacity, the firm 2 can stay out or choose small investment or large investment. Well, again, the only thing is though, this is not a simultaneous move game. Firm 1 moves first and then firm 2 observes its action and decides what to do. All right? Well, if only one firm sort of invests, for example, firm 1 stays out, but firm 2 invests more or large, doesn't matter. Well, in this case, it's going to be, the firm 2 is going to be kind of monopolist in this market, all right? So if only one firm stays, it's going to be the only firm. If they both stay out, we assume that they both get zero, all right? So staying out means zero profit everywhere, all right? However, if they both invest, meaning they both in the market, they are going to compete in a Cournot fashion, which means For example, firm 1 invests small, firm 2 invests small. So what's going to happen here is the Cournot game. Cournot game. And you know what Cournot game looks like, right? Firm 1 is going to choose Q1, firm 2 is going to choose Q2, but don't forget, because they both has chosen small, those Q1 and Q2s can be at most 100. All right? So, for example, what if firm 1 chooses small, firm 2 chooses large? What's going to happen? Well, again, Cournot competition, meaning they choose Q1 and Q2. The thing is, Q2 is any number between 0 and infinity, but because it's a large facility, Q1, however, has to be less than or equal to 100. All right? So it's a Cournot competition, but one firm is constrained to produce at most 100. So we never solved Cournot competition with a constraint. All of our analysis of Cournot was no constraint. So here, firms do have, at least some firms do have a constraint. So the question is, as you see, this is a complicated game. And obviously, what is the subgame perfect Nash equilibrium strategy here? So what is the SPNE strategy outcome? All right, and strategy profile. Strategy profile. So, well, the game is complicated. Why so? Well, because first of all, as you see, there are a lot of subgames. Well, one thing, so each those Cournot games are just one subgame, right? And so here, for example, there's going to be another sort of Cournot game, but here is just one firm. All right, the second firm is staying out. So one firm production. So it's not really Cournot. It's more like a monopoly problem. But there are 3 subgames here. And then obviously here, the game is out, so there's no subgame. Here, it's going to be only one firm. Here is going to be a one firm, so there are 2 subgames here. Here I have one subgame, firm 1 production. Here I have Cournot game. Here I have Cournot game. So Cournot game, where this time firm 1 is low, large, firm 2 is a small. And here both of them are sort of a large capacity. So I have 3 here, 3 here, and 2 here. So it's 8 subgames here. What else? So this is another subgame. All right, I need to, once I find those Cournot games and monopoly problem solutions, I have to put those numbers and find the optimal strategy for player 2 here, optimal strategy for player 2 here, because this is another subgame, and then optimal strategy for player 2 here. And then once I did this, I have to find the optimal strategy of player 1. So this is how backward induction works, and it has 3 layers. Obviously, the hardest layer is these final subgames, meaning I have to find the optimal strategies, Nash equilibrium strategies and outcomes in those Cournot games and in this one firm production scenarios. So there's going to be a bunch of games I need to analyze here. And then once I did this, I'm going to regenerate this game tree, and then you'll see how I apply the backward induction. Okay, so now let's move to the second round of this problem. Okay, so now in the second part of this question, what I'm basically doing is finding all lost subgames, or Nash equilibrium in all subgames. So, well, there are 1, 2, 3, 4, 5 potential subgames, right? So what are they? Well, only one firm is in the market, in the industry, but it has a small facility. This is not really a game, it's just one firm decision problem. The other alternative is only one firm is in the market or in the industry, but it has a large facility. Again, this is a simple problem. It's not really a game. And then here, the strategic environment, there are 2 large facility firms in the industry, and there are 2 small facility firms, and then 1 large, 1 small. Well, which one is large, which one is small is irrelevant, because both firms have exactly the same profit function, meaning once I solve this 1 large, 1 small facility, once I solve this subgame, it is actually give me the payoff and the optimal strategies in 2 subgames, where in one subgame, firm 1 has small facility, firm 2 has large capacity, and then in the second subgame, the other way around, all right? So, because again, because the firms are identical, it really doesn't matter the name of the large or the name of the small firm, okay? So, let's start with the first one. Only one firm is operating in this industry and it has a small facility. So how do I solve its optimization problem? Well, simple. By the way, should we give a name for this firm? You don't have to, but if you like, you can give one without loss of generality because the name doesn't matter. Because again, both firm has the same cost function. So the small firm, meaning a firm with a small facility, is going to have this profit function, whether it's firm 1 or firm 2. So we don't really need to give a name, but if you want to, that's fine. Let's name it as 1, okay, without loss of generality. So pi 1 is what? Price times quantity. So 900 minus Q1 minus Q2. Well, Q2 is 0, right? Because there is no firm 2 in this market, in this industry, times quantity of firm 1 minus no cost. But don't forget, there is the sort of a fixed cost. There's no variable cost, but there's a fixed cost of $50,000. Okay, so if you want to maximize this, what is the profit maximizing quantity? Well, del pi 1 divided by del Q1 equals 0. So this is the first order condition. There's only one condition. So therefore, conditions I erased S for that reason. So what do I have here? The derivative is 900 minus 2Q1. The derivative of 50,000 is 0, is equal to 0. So you see what? Q1 is equal to 450. So therefore, that means pi 1 is going to be 900 minus 450 times 450 minus 50,000. So if you do this calculation, I already did, so I'm going to cheat here. It is equal to, oh yeah, I'm sorry. So there you go. So you have to be very careful about it. So this is not it, right? So I made a mistake. So let me correct it. So here, this is the firm with a small facility. So what I found is the following. The profit maximizing quantity is 450. But there's a very important but here. Remember, the small capacity firm can produce quantity at most 100. You can't produce more than 100. So what does that mean? That means, yes, this firm would like to produce 450 units, but it can't. So does that mean that Q1 has to be 100? Well, for this, you have to check the following. What is the second order condition? If you look at the second derivative of this profit function, it's minus 2. So what does that mean? That means this 452 is actually the maximum, which means the profit function is something like this, 450. All right? Because of this, it is the unique, and because there's only one critical point, and the second derivative is negative, which means it is the global maximum, right? So therefore, this is what the profit function will look like, which means, remember, 100 was the limit. You can't produce more than 450. So therefore, the profit maximizing quantity, right? So that means from 0 to 450, profit is increasing, and then it must be decreasing so that 450 is the optimal solution. But you cannot produce more than 100, so that the maximum profit you can achieve is if you produce 100 units. Hence, Q1 has to be 100, not 450. So then, in this subgame where only one firm remains and this firm has small capacity, it's going to produce 100 units. But what matters, to be honest, is because in this game I am going to calculate particularly the subgame perfect Nash equilibrium outcome, but keeping the strategies sort of well defined is also a good option. So the profit, that's what I need to calculate, is 900 minus 100 times 100 minus 50,000, which is the fixed cost. So therefore, the profit is going to be $30,000. Okay, so I'm going to erase all this and basically put the following. So only one firm with small facility, Q is going to be 100, pi is going to be 30K. All right, I'm just taking a note, writing the optimal strategy and the payoffs. All right, only one firm remains with the large facility. Well, that's simple. There's going to be no constraint. And actually, we did solve this problem, right? I mean, the profit, if you like, again, it's firm 1, is equal to price 900 minus Q1, there's no Q2, times Q1, minus $175,000. But you know what? The first order conditions, there's no S, is going to give you again Q1 equals 450. So the first order conditions always look at the marginal conditions, and so the fixed parameters are irrelevant. So for that reason, the optimal Q will still be the same. And now we do not have to worry about this limit, because remember, when the capacity is large, Q can be any number between 0 and infinite. And so therefore, in this case, firm is going to produce 140 units, and the profit is going to be, therefore, instead of Q1, I'm just going to plug 450, but the cost is not 50,000. Be careful about it. And if you do this calculation, actually, you see that 27,500K. All right? So 27.5K. So $27,500 is going to be the profit. Well, apparently, being a large firm is not so profitable. All right. Now we are actually getting a more complicated environment. What if both firms have large capacity? So that means the following. This is no longer the profit function, because there are two firms in the industry and both have large capacity. So profit of firm 1 is 900 minus Q1 minus Q2, don't forget that, times Q1. Minus 175,000, and pi 2 is symmetric, right? 900 minus Q2 minus Q1 times Q2 minus 175,000. So I am going to maximize, and so the first order conditions means solve this, del pi 2 del Q2 equals 0. So if you solve this, what do you get? You have 900 minus 2Q1 minus Q2 equals 0. And if you solve this, you have 900 minus 2Q2 minus Q1 equals 0. So that means Q1 equals 450 minus Q2 over 2. And Q2 equals 450 minus Q1 over 2. So solve these two equations to find these two unknowns, Q1 and Q2. How do you do that? So whenever you see Q2, just plug it here. So I have Q1 equals 450 minus 1 over 2 parentheses, 450 minus Q1 over 2. So that means Q1, again, I'm going to cheat because I already calculated that. So Q1 is equal to 300, and Q2 is equal to 300. All right, so the Nash equilibrium, when both firms are in the industry and they both have large capacity, remember, they do not have any constraints. They can produce any number of output. So Q1 equals Q2 equals 300 units. What's going to be the profit? Well, just whenever you see Q1 and Q2, just plug those numbers. I already did this. So pi 1 equals pi 2, which is equal to minus 85K. So actually, both firms being in this industry and having a large capacity is going to be a horrible outcome. All right. Well, now, what if both firms have small capacity? All right. So here is one thing. What's the difference? Well, here the difference, I'm not going to erase this entire thing. I'll just sort of revise them. Well, both firms are operating, and so 900 minus Q1 minus Q2 times Q1, Q2 stays the same. Only the cost, the fixed cost will be different, right? Instead of 150 as 175, I'm going to have 50K. Okay. Is this going to change my first order conditions? No, because the first order conditions are irrelevant of constants. So these are going to stay the same. So does that mean that my best responses will be the same? Yes. But you know, the question is, can I solve them and find Q1, Q2 equals 300? No. Or let's put differently, does that mean that, before constraints, they actually would like to produce 300 units, but because they can produce at most 100, does that mean that 100 is the Nash equilibrium of this game? For this particular question, the answer is yes, but in general, you cannot conclude like this. You have to draw the best responses and find the Nash equilibrium in this case. All right, so that's the safest way, trust me. In this question, I mean, the answers will be yes, Q1 is going to be equal to Q2, which is equal to 100, all right? And then whatever the profits are. But in general, this is not true. So here, what does that mean? So these are the best responses. Okay, so how do we graph the best response functions for these two firms? Well, simple, as we usually do, draw Q1 versus Q2 graph, right? So these are the strategies for firm 1 and firm 2. Well, don't forget, both firms have small facility, and so their constraints are 100. They cannot go above 100. So that means do not really worry about what if Q1 or Q2 is higher than 100. It can't be. All right, so the question is, so now I'm going to draw the best response of firm 1 first. So what does that mean? That means when Q2 is equal to 0, for example, all right, well, the Q1, the maximum number it can be is 450. Well, obviously this is impossible. So when Q2 is 0, Q1 is going to be 100. Okay, when I increase Q2, all right, all the way up to 100, for example, so when Q2 is equal to 100, that's equal to 50, 450 minus 50, which means 400. But again, firm 1 cannot produce 400 units, so therefore it's still 100. What does that mean? That means for all the values between 0 and 100 for Q2, the optimal Q1 is in fact 100. Are you following me? I mean, the optimal Q1, the profit maximizing Q1 is in fact 450 minus Q2 over 2. But all of those, for Q2 values that are less than 100, all these numbers are higher than 100. And we know that firm 1, although it wants to produce higher than 100, it cannot. So therefore, the profit maximizing, the best response strategy for firm 1 is 100. Well, symmetrically, you don't really have to do the same sort of thing again, but symmetrically, so this is best response for firm 1. And best response for firm 2, let's use a different color, is going to be for any Q1 level, the best response is Q2 equals 100. So that means those two best responses intersect at just one point, and hence that is the only Nash equilibrium where both firms produce 100 units of output. All right, so if two firms are in the market and they both have small facility, they both are going to produce 100 units of output, and then what is going to be the profit? The profit for each is going to be pi 1 equals pi 2, which is equal to $20,000, $20,000. All right? So the one last final subgame that I need to find is what if one firm is large and one firm is small? Okay, let's see how things are going to be different. So let's say the name is irrelevant. All right, be careful. So let's say firm 1 is the small firm, firm 2 is the large firm. So here its profit is going to be different only with this minus term. The first order conditions will be the same. The best responses will be the same, right? Because, right? I mean, it must be because the first order conditions are the same. So then all it comes to the point of how do we draw the best response of firm 1 and firm 2. Don't forget, Q1 here has to be less than 100. Q2 can be anything. So how do I gonna draw it? So this is what I'm going to do. So once again, this is Q1 versus Q2 graph. So let's say, remember, Q1 can be at most 100 and Q2 can be anything. All right, so something like this, it goes to infinity. So here, let's draw the best response curve for firm 1. So for Q2 0, I know that the best response is 450 units, but it's impossible. So firm is actually preferred to produce 100 units. All right. Once again, I am sure about this because we already checked the second order conditions. So the profit function is increasing all the way up to 450. So 450 is the profit maximizing. All the other smaller quantities are this is like what the profit function will look like. So this is 450, all right? 450 minus Q2 over 2. And then below this, it's decreasing. Above this, it's decreasing. And so therefore, the best response is going to be 100. All right? So that's that. And how do I know that? Well, because this is the first derivative of the profit function, and therefore the second derivative of the profit function with respect to Q1 again is minus 2. All right, so therefore I know that these profit functions are decreasing. All right, so here is the thing. So when Q2 is equal to 0, the best response is 100. Well, it is going to be 100. The best response will continue to be 100 up until what point? Well, when Q1 is equal to 100, right? Q2 is 450 minus Q2 over 2. So Q2 over 2 equals 350. So Q2 equals 700. So until Q2 is equal to 700, the best response will continue to be 100. Well, once Q2 is above 700, Q2 is getting large and large and large. Well, this time Q1 will start decreasing. All right. Well, what's going to be the point where it intersects this vertical axis? Well, it's the 900. How do I know that? Because when Q1 is 0, Q2 is equal to 900. So therefore, this is what best response function for firm 1 will look like. So now the best response function for firm 2. Well, that's simple because there's no constraint for firm 2. So when Q1 is 0, Q2 has to be 450. Let's say 450 is here. And when Q2 is 0, Q1 has to be equal to 900. So let's say 900 is here. So this is what it's going to look like. All right. So therefore, the Nash equilibrium point is going to be somewhere here. So what is this point? Well, this point is where Q1 is 100. All right, Q1 is 100, and Q2 is equal to, therefore, just plug 100 here. Q2 is equal to 400. It looks like 406. All right, so this is how much Q small, let's call it. Q small is going to be 100. Q large is going to be 400. Therefore, profit of the small and the large firm are going to be, so these are all Nash equilibrium of those subgames. And okay, so the small firm's profit is going to be minus 10K and the large firm's is minus 15K. So that's basically it. We found the Nash equilibrium outcomes and strategies in all the subgames that follows the firm's entry decision. Now let's build back the game tree and then start working on the backward induction and see whether firms are going to choose not to enter or enter with a small or large capacity. So it's coming up next. Okay, so now this is what our game will look like. Remember, firm 1 first decides whether to choose a large capacity, small capacity, or no entry. And then after observing firm 1, firm 2 decides exactly the same thing, whether a large capacity, small capacity, or no entry at all. So now all I have to do, and then they play the Cournot game. If there's only one firm, it's just monopoly problem. If there are two firms, it's a Cournot problem. So we found the Nash equilibrium and or the optimal solutions. So here, all I have to do is just pull up those profit numbers and place them into this game tree. So here, for example, if they both, so in this sort of branch, both firms enter and they both have the small capacity, all right? I'm sorry, large capacity. LL means large capacity. So it's a too large facility. So the profits are going to be minus 85K, minus 85K, all right? So I'm not going to write thousands. Okay. Well, what about here? So one firm is large, one firm is small. So one large, one small. So we know that the small firm is going to make, so the small firm is the second firm. So it's going to make minus 10. The large is going to make minus 15. And finally, here, large versus no entry. That means only one firm is on the market and it has large facility. And we know that it's going to be it's the first firm, so it's 27.5K. And the second firm, because it did not enter, its payoff is 0. All right? So fill out the rest. How so? Firm 1 is small, firm 2 is large. So it's basically the opposite of this scenario. So firm 1 is small, so it's minus 10. And firm 2 is large, it's minus 15. Small, small, so they both have small facility, so it's 20K. And then small, no firm, and so 30K for the first firm and 0 for the second. And then finally, no entry, we already know that that's 0, 0. And all of those, the first firm has 0 profit. And then the second firm has a large, in this case, 27.5, and in the small case it's going to be a 30K. That's it. So this is what the game will look like. So in this subgame, what is the optimal decision? So now I'm using the backward induction, and then we'll find the SPNE. So here, the second firm clearly prefers not to enter. If the firm 1 entered with a large facility, it prefers not to enter because 0 is higher than others. Here, if first firm enters with a small facility, clearly the optimal strategy to enter with a small facility for the second firm. And here, the second firm's optimal strategy is clearly the small if the first firm did not enter. And then now, what is the first firm's optimal strategy? If it chooses large, it knows that the firm 1 knows that firm 2 is not going to enter, and so it's going to get 27.5. If it chooses small, it's going to get 20. If it chooses not enter, it's going to get 0. So you know what? The optimal strategy is to go in with a large facility. So basically, by choosing first, you scare your opponent, and instead of going with a small, you actually go with a larger facility and scare the competition hell out of the second firm. And so instead of sharing some profit, you actually share the entire profit by itself. But obviously, the total profit here is 27.5, here is 40. So that's more efficient outcome. But unfortunately, more efficient outcome is not going to be the equilibrium outcome, because this is a monopoly. All right, so, and in fact, you do see this in real life, right? The firm 1, instead of entering this firm, a market industry with a small facility, and the other firm is also small facility, and they compete with each other. And so this is more like perfectly competitive market, and so it's sort of more efficient. But no, they prefer a higher profit for themselves, so they invest in a bigger project and basically eliminates the competition. So here, the SPNE outcome is therefore firm 1 chooses large facility and firm 2 chooses not to enter at all. And then firm 1 produces Q1 equals, because it's a large facility, 450 units. And obviously firm 2 does not produce anything because it's not in the market. So that is the subgame perfect Nash equilibrium outcome. Well, what about the strategy? Well, strategy is more complicated than this. The strategy, I'm not going to write it, but I'm going to read it. The subgame perfect Nash equilibrium strategy is the following. Firm 1 enters with a large capacity. Firm 2 does not enter if player 1 plays L. It does enter with a small capacity if firm 1 chooses S, and S if firm 1 prefers not to enter. And then again, I am talking about subgame perfect Nash equilibrium strategy profiles. The quantities that in all these 1, 2, 3, 4, 5, 6, 9 subgames, the quantities will be as follows. For example, here, large, the quantities are going to be both firms producing 300 units. In this subgame, meaning firm 1 has chosen large, firm 2 has chosen small, while the quantity of firm 1 is going to be 400, quantity of firm 2 is going to be 100, etc. All right, so that very long description of the strategy is what we mean by subgame perfect Nash equilibrium strategy profile, but it's too long, and well, what's the point of knowing this entire strategy for this particular game? It's more interesting. The relevant thing that we need to know is what the outcome is going to be, and this is what subgame perfect Nash equilibrium outcome will be in this game. So that's it.